Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we are going to look at the actual implementation of decision tree classifier using Scikit-learn in Python. In previous video, we looked at the intuition behind decision trees, Gini, impurity, entropy, and we'll be using all of that in this video with simple 1 or 2 lines of code. So let's get into Jupyter Notebook and see how we can code. Here I've imported several libraries. As you can see, uh, this is the tree library that we'll be using, and we have matrix and train test split. And additionally, I've gone ahead and imported all these classifiers as well. And the reason is because what we'll try to do is we'll create synthetic data, and we'll try to make it more complicated and see how each of these classifiers perform in comparison with the decision tree classifier. So the very first step that we'll do is we'll create a data set. So say n is equal to 0.3 plus np dot linspace 1 to 10, and let's have maybe just 20 data points, and we can create a part of a circle. So circle is equal to np dot array, and here np dot pi multiplied by np dot sin n, and then the second one is np dot pi multiplied by np dot cos n, and take a transpose of that. Now if we try to plot this, plt dot scatter circle and all rows and first column, and again we have circle, all rows, and the second column. So we plot this, we get a circle, and it's stretched out because the way this is not a rectangle and it's plotting this as a square. But that's what we are trying to do. We'll split this circle and create two separate halves, and we'll also add noise to this. So let's go ahead and create noise. Initially we'll leave the noise as 0, and later on we'll add random noise there. So np dot random dot rand n, length is n, so same number of records. And then how much noise do we want to add, so we can control that by using this parameter, how much. Now what we'll do is we have these values in the circle, so we can, to make it easier to type, I'm going to put all the values from the first column in here. So circle and column 0, so that's the first column, plus how underscore much, how much noise, so we are adding noise to this. And then again we have b, this circle, so this we can call it x and y for now. We'll override those xy values later on if we have to use them again. How much uh, into noise. So now we have added the xy noise to this. Now if we try to plot x and y, we should be able to see the difference. So here uh, uh, because the noise is 0, if we change this, and if we add this, say 0.5, then because these are less number of, let's say we increase the number of data points to 100, so now we have these here, and sorry, we need the np dot random there. So now if we add noise, this is what we get. So let's keep moving forward without adding any noise here. So we're just going to add 0 there, so we have no noise. Next, what we'll do is we need to stack all these up. So I'm trying to create a data set with 2 C's and a diagonal line. So for this, we'll save this as C1. So np dot horizontal stack, and here we have x, we have x minus x, x minus 1, and then c2 is equal to np dot horizontal edge stack, and this is y minus y and minus y to the power into 6. So those are the uh, um, two columns we created for x and y features. So if we now try to plot c1 and c2, you can see that there are these two circles that are created. Now we'll split those circles, and for that what we can do is change this addition sign to multiplication, and I'm going to reduce these to just 10 numbers. So now we have these separated out circles, and to this we will later add um, diagonal data points also. So for now what we can do is we'll group each of these segments into different classes, and to do that we'll have to create a y variable, and let's before that we can plot them in different colors. So let's try that. So this would be plt dot scatter, and now we have c1. So c1 and c2 are together. So let's probably we should first create the y labels. So what we'll do is we'll put these in a bigger array. So np dot v stack, and within this we have c1 c2 dot transpose, and if we print d dot shape, so we have two columns of 300 records, and so this is d dot shape, and now what we'll do is put the y labels on them. So y underscore target is equal to h np dot h stack, and here we'll create np dot zeros. So the first class would be labeled 0, and then we have the second class which is 1. So np dot ones y dot shape, and then we create the third class. So 1 plus np dot ones y dot shape, and later on we will create additional classes. So for that I'm going to create this one and leave it as commented. 2 plus this would be the third class, np fourth class, np dot ones y dot shape, and with that we can put all of this information now in a data frame. So df is equal to pd dot data frame, and here we have np dot h stack, and we are going to stack the this one and the y. So we have features, so these are essentially the features that we have. So these are the features, and then this is the target label. So here we are going to stack d comma y underscore target, and for target we'll reshape this to -1 by 1. So just need a column, and after this we'll add the column names. So columns is equal to we'll give them names, features x1, then the second feature is x2, and then the target is y. And now if we print shape of df dot shape, so we see that it is 300 by 3. So we have two features and one target. So df dot shape. So with that, now we can try to plot different data points with different colors. So let's see how they look. Plot plt dot scatter, and the very first one is df. We can look at the head. So df dot head, we have these, and if you look at df dot y dot unique, we have 3 different classes right now. So first we'll plot the class 0. So df and y is equal to 0. And so for x-axis, we have the feature which is x1. And then similarly, we can get the y. So for this, we'll need to use the the lock, because we are using the column name in index. And I copy this and paste it here. And this would be feature 2. So when we plot this one, we get that plot. And so let me cut this and put this below cell, so we don't have to run that data frame over and over again. So this is what we have now. We'll plot the other classes on top of this. So the second one class will be, we just change this value to 1. So that's the second class we have. And then the third class we have, it has a class label 2. And so we add that there. So class level 2. So this is the data set now that we are trying to classify. So we have 3 classes, and we can see that they have a peculiar arrangement, more like a circle inside a circle. And we'll see how these classifiers perform to uh, find the 3 classes. Now what we can do is, as usual, we'll split the data into train and test sets. So here we'll split the data, and as you'll see, we'll progressively make this data set more and more complicated, and so that you'll see how the classifiers work in those situations. Y underscore test is equal to train underscore test, train underscore test underscore split, df dot drop. So from df we do not need the label column, so I'm going to drop that one, and we drop it along the axis 1, and that's the x we have. And then df dot y, that's the y, and we just use shuffle is equal to true. I think the default for shuffle is always true, and we can check how many rows are there in each of these. So print x underscore train dot shape, x underscore test dot shape, y underscore train dot shape, and y underscore test dot shape. So we have 225 in train set and 75 in the test set. So initially, so let's look at the models. Now for modeling, what we'll do is, first we'll create a model list of the classifiers, and then we'll use those. But before we do that, we'll simply go ahead and run the decision tree classifier. So decision tree classifier and criterion. So the default is, I think, Gini, so we can try that one. And we'll set the class weight is equal to balanced, balance. Okay. And clf dot fit x underscore train, y underscore train, then y underscore pred is equal to clf dot predict x underscore test, and then we can get the accuracy, which is matrix dot accuracy underscore score, y underscore test, y underscore pred. And we have the confusion matrix. So cm is equal to matrix dot confusion underscore matrix, y underscore test, y underscore pred, and we can print these values. So we have the accuracy score, that is equal to ACU, and then we have the confusion matrix. So print confusion matrix, and we'll add a new line there. and this would be just CM. So when we run this, as we can see, we get the 100% accuracy with with the decision tree classifier. We see that all of the classes were correctly classified, and so it is able to find all of these correctly. Now let's see how. And while this is one, you always have to remember that this data set, when working with the decision tree, there is one of the disadvantages of using decision trees is overfitting, and this could be very well an example of that. So now what we'll do is we'll create a model list and see how different types of algorithms perform on this classification task of nested circles or nested segments. So tree dot decision tree classifier, I'm adding this one back again in there. Decision tree classifier, and the next one we have is naive Bayes. So naive underscore Bayes dot Gaussian naive Bayes that we looked at in the previous videos. So all these classifiers that we'll be listing here, we have covered them in previous videos in this series. So I want to check, if you haven't already, you could check them out so that you have a background intuition of how they work. Classifier, and here we have Gaussian process classifier, and the next one is KNeighbors, so KNeighborsClassifier, and so let's call this KClassifier. Let me copy the word classifier, and then we have SGDClassifier, so SGDClassifier, and so this is SGD, and the next one is svm.svc, support vector classifier, svc, and we have linear discriminant analysis, and here this is linear discriminant analysis, and I'm going to copy all of this, paste it down here, and we'll also add the quadratic discriminant analysis. And finally, the very first classifier that we learned was the RidgeClassifier. So let's add that, linear model.RidgeClassifier, and we have RidgeClassifier. So these are all the models that we have, SGD, and so these are all the models we have. What we'll do is we'll run them in the default settings. So we haven't tuned any, and we are not going to try tuning each of these. Let's see what is the base accuracy when we run all these models on the task of classification with a data set that looks like this. So here we'll put all of this in a for loop. So we'll add the for loop up top here, for classifier, and the name in model underscore list. Here we don't need that line. I'm going to delete that. So we fit, then predict, get the accuracy matrix, and just to make it visually easy, I'm going to add a print statement here. So print, and within this, going to add just a bunch of dotted lines, and then I print the name of the classifier, and then again print the dotted lines there, and then finally here just add a new line so they are well separated. So now when we run this, here is the output. So we can see that decision tree classifier this time when we used with the default setting, so here we did not specify if we need class weight balanced or criterion is Gini. I think the criteria here is still Gini, which is the default. We have 0.98 accuracy, or 986. Then for Gaussian naive Bayes, we have some misclassifications here, so the accuracy is 0.88. Gaussian process classifier is 100%. KNeighbors is 100%. SGD is 0.82, and SVC is not working. So let's look at what SVC, what we missed in SVC. All right, we missed the parenthesis there. Okay. And so SGD is 0.77. There are several misclassifications there. SVC is 1 in LDA and QDA. So QDA would perform better. So it is at 0.9. LDA is at 0.7. And RidgeClassifier is probably the lowest at 0.62. And that is expected with this type of data, where there is no linear way to separate this. Even if kernels are used, it's still not able to separate. Maybe if we tune the RidgeClassifier, it could improve this accuracy for this data set. Now what we'll do is we'll add noise to this data. So we'll move these around and see how classifiers perform on that type of data. So I'm going to comment that out. Now we have the noise added there, and now when we plot this, the data looks like this. And what we can do is we can add here increase the number of data points. I'll change this to 500, and so now this is how our data set looks like. We have several data points, and they are the classes are overlapping in some instances. So we'll set the alpha to 0.5 in both the cases. So let's add that here as well, and add that here, and run this. So with this new data now, what we have is we have more number of data points, but then we also have noise. And here we can see that there is some overlap of the green color dots with the blue dots, while the orange dots seem to be completely separated, except maybe 1 or 2 points down here. So let's run the classifiers again and see how well they perform. So here we have all of these, and previously, as we can see, these were 0.97, 9.88, and these were 100%. Now when we run this, as expected, we see a drop in the accuracy, but still decision tree is at 0.957. Gaussian naive Bayes has dropped down, is at 0.91. And then we have the Gaussian process classifier, which is at 0.95. So these are KNeighbors is still doing pretty good in spite of all the noise. And we can see that SVC is also doing pretty good. These, though, the ridge is expected is going down. The quadratic discriminant analysis, it is still close to 0.9, and that's how the accuracy changes with adding so much noise. If we add, so you can play around with this, you could add more noise and see what happens. But what we are going to do now is here we'll add a few additional data points, and this is for adding the diagonal. And so we'll create diagonal x1 is equal to np.lin space, and this would be C1. So we'll stay within the range of what C1 is. So C1 dot min, C1 dot max, and length would be the same n that we started out with. And then we have diagonal x2 is equal to n, this would be diagonal x1 plus we'll add the random noise. So 0.8 into np dot random dot random rand n, and again length is diagonal underscore x1, and finally we have c1 is equal to np dot h stack, and we stack the c1 with this diagonal x1, and then we can stack c2. Similarly, c2 is equal to np dot h stack, this would be c2 and diagonal x2. And after this, what we need to do is change this, the y target. So we add this last set of data points labels, that would be class 0, 1, 2, and then 3. So when we now run this, we have these 3 classes, and we can plot an overlay of the the fourth class that we have created on top of this. And as you can see, this class is going across the entire data set, and it has substantial noise. So what we can initially try to do is reduce the noise. So let's try. So we have lesser noise there, and let's see if how the classifiers work with this type of data set or intermingled classes. And here, as we can see, if we run the decision tree, the accuracy in this case drops to 0.88. And let's run all the classifiers now and see what output we get. So here decision tree is 0.87. The Gaussian naive Bayes has dropped substantially. The Gaussian process classifier is 0.88, which is still higher, and the KNeighbors is performing really well. It is able to identify that the diagonal line as a separate group. That's pretty awesome. And then we have SGDClassifier, SVC is there. Linear won't perform. Then quadratic is still doing a pretty good job, and the RidgeClassifier is just it's not going to work in this case. With this, what we can try to do now, if we add further noise, so that's going to make this data set even more complicated, and but it'll give us a chance to see how these different classifiers perform in such situations. If we add that and take that up to 0.8, and now look at this data set, we see that there is substantial noise in the data now, and the diagonal red dots are completely overlapping the entire data set space. So that's an issue, and let's see how the classifiers work with this current setup. Now let's run this one, and I'm going to go through this print test split, and we have now the decision tree classifier by itself, it has gone down to 0.79, and that is expected. So you'll see the accuracy score drop significantly, and the misclassification has increased a lot. Still, the Gaussian process is doing pretty well at 0.86, and it's and the same as with KNeighbors. They are the best performing even in a situation with this noise. And the SVC linear LDA is low, and the rest are pretty low. So that's how different arrangements of the classes would change how the algorithms work. Now, what we can try to do is see if we can tune. We won't do the cross validation, but we can at least look at how if we can change any parameters to improve the accuracy from 0.79 with so much noise in the data. And to do that, we can always look at the help menu and see what parameters we can change. And here, as we can see, the first parameter we can try to change is the type of criteria we use. So if we use the entropy, would that help? And then we can change the maximum depth. So if it is overfitting, we can change that. So let's put a max depth of maybe 10, and min samples per leaf. So this is currently 1. So we can change the min samples to avoid overfitting. We can change that to maybe 3 leaves. And with those additions, let's run this again. And so now, as you can see, we improved the accuracy scores slightly. So it was 0.79. Now we are at 0.82. So if you run a cross validation on this and look at all of, you could tune all of these and then see which of these parameters work best for getting the best accuracy. Let's close this one. And that was it then for this video. I hope you enjoyed this video. Although this was a third data set, it was not an especially easy data set to classify because of the overlay of different data points. If you want to practice, you could try to tune each of the models that we have in the model list and see which one of these models could perform the best for classifying this type of data. If you have any comments or suggestions, please let me know below. If you would like me to make more videos on this type of data sets. I hope to see you all in the next video. Until then, please like, share, and subscribe. Thank you.